Welcome, everybody, to another episode of What's Up with the Universe. Yes, I am your host, Eli Hugh, and welcome, everybody. I know it's been a while, but I've been having some computer problems, and I need a mental break from this lockdown. So, I want to thank everybody who's joining me here or on watch, or if you're rewatching this stream. Thank you for subscribing. Yeah, I know that is a very good idea. We should observe the sun by night so we don't get burned. I mean, have you ever actually woke up this morning or any other morning, went outside and looked up or looked out the window and go, "Why is that big old bright yellow ball in the sky?" Well, that is our sun. Yes, it is. Believe it or not, that is our sun. It is one of many different types of stars in the universe. I mean, stars basically, they're huge balls of hydrogen and helium that are formed in galaxies from a great big cloud of gas and dust over billions and billions of years. I mean, like I just said, the sun itself is a star. It's our very own star. I mean, you ever wondered how many stars are in the universe? Well, you can take a billion and billion and billion trillions, and you still want to have the exact answer because no one knows. I mean, there are different types of stars in the universe, from protostars to red supergiants. I mean, they can be categorized by mass and temperature. Stars are also classified by their spectra, which is the elements that they absorb, along with the brightness, which is apparent magnitude, and the spectral class of a star can tell astronomers a lot about it. Oops, wrong button here. I mean, stars themselves, they are massive and basically luminous hot plasma balls. In case you're wondering what a plasma is, it's a gas that is so hot that the nuclei itself and the electrons of the atoms have separated. So it's eventually a hot soup that contains positive ions, which is the atom and nuclei, and electrons. I mean, stars basically consist of about 70-75% hydrogen and about 25% helium, and of course some heavier trace elements. Depending on the composition, any star can vary significantly, depending on the age of the star and whether it was born in the early times of our universe or just more recently. I mean, the sun, for example, our own sun, is composed of about 74.9% hydrogen, 23.8% helium, leaving less than 2% for all other heavier elements other than helium. I mean, during the lifespan, stars generate radiant energy by fusing hydrogen into helium. It's a process that converts mass into energy and releases energy in the form of radiation of various wavelengths. I mean, in order to maintain the nuclear fusion in the cores, stars have to have a temperature ranging from 4 million to 40 million degrees Kelvin. I know, that's very hot. Sorry. Got a little question here. Let's see. Will people do questioning if they question the intricacy of proof for us? You can believe in what you're saying, which is kind of BS. How do you know the plasma balls? Because you never had any observation, which is sorry. You're going based on what your mainstream society tells you. I'm not going off what mainstream society tells me. I'm going off with the several probes that NASA and ESU has launched. And I'll get into some of those probes in a little bit if you want to pay attention and stick around and find out exactly how NASA obtained this information that I'm sharing with everybody here. We're going to talk about next is the size of our sun. The size of our sun, it's just an average sized star. I mean, there are bigger stars out there, and there are smaller stars. We found stars that are about 100 times bigger in diameter than our own sun. I mean, take Canis Majoris 1. If our sun was the size of a rice grain, Canis Majoris would be the size of a 10-inch pizza pan. That's how big that star is. The sun is the largest object within our own solar system, comprising about 98.8% of the solar system's mass itself. It's located about 93 million miles from Earth. The sun's magnetic field itself, it spreads throughout the whole entire solar system, known as the solar winds. With a radius of about 432,000 miles or 700,000 kilometers, our sun is not that very big, like I said, but it's still more massive than Earth itself. Scientists estimate that about 332,950 Earths will match the mass of the sun. I mean, you need about 1.3 million Earths to fill it. Like I said, it's about 150 kilometers from Earth. The nearest stellar neighbor to us, another star, is called Alpha Centauri. It's a triple star system. Proxima Centauri is about 4 light years away. Alpha Centauri A and B, which are two stars orbiting each other, they are about 4.3 light years away. In case you're wondering what a light year is, it's the distance which light travels in 1 year, which is about, let's see, 5,878,499,810 million miles an hour or kilometers. Sorry, I have the exact number on me. Numbers. Okay, yeah, the more you intake, the more mass you get. That's true. I mean, for what we've known and what we have studied, there are 7 different classifications of stars. That means 7 types of stars, temperatures: O, B, A, F, K, G, and M. These stars range in color from blue to white, orange to red. I mean, all different stars have different colors and temperatures and different characteristics. I mean, some of the main sequence types of stars, like I said, the O's, B, and A, these are blue stars, like Rigel and Sirius. F stars are blue and white stars, like Tricon. Orange and red, like Aquarius. And M, red star, like Betelgeuse. And of course, we have our own star, G star, white yellow star, which is known as basically our sun. What scientists have discovered through different models and creations and observations is how a star is made. It begins with a massive cloud of dust and gas when it starts to collapse and break down. I mean, how does this happen exactly? Well, it happens through the force of gravity. And then what happens next is nuclear fission. See, okay, I'm going to try to break this down easily so you guys can understand, because I'm not going to act like this is a college advanced class in physics. I'm going to try to break this down easily so you can understand what nuclear fission is. There are 2 main processes of energy conversion in the core of stars. The first is called the proton-proton chain, and it is dominant in stars up to the size of the sun. The second one is called the carbon-nitrogen-oxygen cycle, or CNO cycle. That prevails in stars that are more massive than 1.3 times the mass of our sun. The fusion rate of both the process highly depends on both temperature and pressure. A small increase in temperature leads to a much higher fusion rate. See, fusion happens in very large clouds on gases called nebula. When nuclear fission starts in a nebula and reaches a temperature of about 10,000 degrees or so, the star itself begins to form. This new baby star right here that we actually it's starting to form, that we know of, we call it a protostar. It's a star that's the protostar can, in its very long life, live on the universe like a long, long time. I mean, gravity continues to play a part in the star's birth continuous life cycle of millions of years. This mass of solar determines the color of the star, which allows scientists to categorize the type of star. Scientists then they can also try to conform the amount of energy the star can give. And there is no such thing as pixie dust unless you're in Never Never Land. I know that second star to the right and straight as the morning, but didn't actually classify what type of star to go to. So, hey, maybe we're both right. Who knows? The proton-proton chain, the PP chain. This is a process that converts 4 protons into 1 helium nucleus. The process is demonstrated right here, as we see in a little diagram. In the hot and dense cores of the stars, 2 protons, a proton is the same as the nuclear level hydrogen atom, sometimes they crash into each other, forming a very unstable element called helium-2. I mean, normally this element almost immediately decays back into 2 protons, but once in a while, during the extreme short period in which helium-2 exists, one of the protons decays into a neutron, emitting a positron. I mean, the electron's ampliparticle, or in other words, the antimatter counterpart, and a neutrino. This process is basically called the beta plus decay. So basically, we now have 1 nucleus and 1 proton and 1 neutron, and the resulting reaction is the deuterium. The positron that arose out of the beta plus decaying almost immediately annihilates with an electron. Remember, stars are composed of plasma, so there are lots of free electrons flying around it. This basically is creating 2 gamma rays. Okay, the deuterium, it fuses with another proton, forming helium-3. It's a light isotope of helium, which the moon is very much covered with. Throw protons make a ghostbuster, proton packs make a ghostbuster. Not throw protons. You get your nerd card revert file, Mike. Oh, now you got me all set. Let's talk about it. Oh, yeah, H3. After that, the process again is releases a gamma ray that heats up to the sun's core, and the helium-3 finally fuses with another helium-3 isotope, forming a stable helium atom, or so-called alpha particle. These two protons are released during the final step. I mean, they'll have a second chance to become helium in the PP chain. Of course, like every star in the universe and our own galaxy, it's going to run out of energy. Yeah, like I am. That's why I need a little drink. So, when suns start to die, it will swell up so big that it will engulf Mercury and Venus and maybe Earth. I mean, scientists predict the sun is a little less than halfway through its lifetime and will last another about 5.5 billion years before it shrinks down to a white dwarf. Let's talk about the structure of our sun. The sun, like any other stars, like I said, is a ball of gas. In terms of the number of atoms, it's made up of 91% hydrogen, 9% helium, and the sun has 6 regions. It has the core, the radioactive zone, and the convective zone in the interior, the visible surface, called the photosphere, the chromosphere, and the outermost region, the corona. We won't want to miss Mercury. Yeah, I still want to declassify Mercury as a planet. And Bird of Prey 5 knows why. Okay. The sun's basically enormous mass. It's held together by a gravitational attraction, producing an immense pressure and temperature at its own core. At the core itself, the temperature is a striking 75 million degrees Fahrenheit. That's enough to instantly cook a marshmallow in half a second, quicker than half a second, which is 50 million degrees Celsius for all you non-Americans. This is actually high enough to sustain thermonuclear fusion. So this is a process which atoms combines to form larger atoms, and in the process release staggering amounts of energy, specifically in the sun's core. Hydrogen atoms fuse to make helium. The energy produced in the core powers the sun and produces all of the heat and light the sun emits that we see. Energy from the core is carried outward by radiation, which bounds about the radioactive zone, taking about 170 to 200,000 years to get from the core to the top of the convective zone. I know. They got to bounce around all over the place. I mean, the temperature itself drops below 3.5 million degrees in a convection zone. So where large bubbles of hot plasma move upwards, the surface of the sun, the part we can see, is only about 10,000 degrees Fahrenheit. I mean, that's much cooler than the blazing core, but it's still hot enough to make carbon like diamonds and graphite not just only melt, but boil. The surface of the sun, the photosphere, it is a 300-mile thick region from which most of the sun's radiation escapes outwards. I mean, this is not a solid surface like the surface of planets. I mean, instead, this is the outer layer of the gassy star itself. We see the radiation from the photosphere as sunlight when it reaches Earth in about 8 minutes after it leaves the sun, which means it takes about 7.5 to 8 minutes for light to reach Earth. The temperature of the photosphere, like I said, is about 10,000 degrees Fahrenheit or 5,500 degrees Celsius. Who is the core, bright or dark? Who? Oh, sorry, I'm reading the last name. Duh. Yeah, who is the core, bright or dark? It's the core, bright or dark in real life. We believe it is bright. We do not know the exact color of the surface of the interior of the sun. So we believe it's really, really bright because of the photons creations. The atmosphere itself of the sun. This right here is an actual image of the surface of the sun. This is the crown, which make up the solar atmosphere. I mean, this is where you see features such as sunspots and solar flares. Visible light from these top regions, they're usually too weak to be seen against the brighter photosphere. But during a total solar eclipse, when the moon covers the photosphere, the chromosphere looks like a red rim around the sun. I should have got an image for the look close for you, but you know what I'm talking about. During the eclipse, the corona forms a beautiful white crown on the outside of the moon, with plasma streamers narrowing outwards. I mean, it's forming shapes that look like flowering petals, basically. Strangely enough, the temperature of the sun's atmosphere increases with altitude, reaching as high as 3.5 million degrees Fahrenheit. We do not know exactly why it gets hotter as it gets away from the sun, because as everybody knows, when you get closer to a fire, you get cooler. But the farther you get away from the sun's corona, the hotter it gets. We think it has something to do with the magnetospheric sphere pushing the solar winds at an altitude, at a rate of speed. So we still do not know this yet. Nobody has a direct answer. There are hypotheses everywhere you go. So until science has the correct answer why this is happening, we just have to speculate and hypothesize. The sun releases a constant particles of magnetic fields called the solar winds. Yeah, this may be the reason why it's so hot out there. I mean, the solar wind, it slams across the solar system in particles and radiation, which streams all the way to the planetary surface of the Earth, outwards in the atmosphere. I mean, the solar winds reach all the way past Pluto, all the way to the Oort cloud. Yeah, that's actually a good question, Mike. Let's talk about the magnetic sphere of our own little sun here. The electric currents in the sun, it generates a very complex magnetic field that extends out into space to form the interplanetary magnetic field. As you can see here on the right-hand side of this animation, this is an actual picture from SOHO probe, a solar flare erupting on the sun. I mean, the sun's magnetic field is carried throughout the solar system by solar wind. Since the sun rotates, the magnetic field spins out in a large rotating spiral known as the Parker spiral. I'm going to get into Mr. Parker in a little bit here. You'll understand a little bit. The sun it doesn't behave the same way as all time. I mean, it goes through phases of its own solar cycle. About 11 years or so, the sun's geographic poles change the magnetic polarity. Basically, when this happens, the sun's photosphere, chromosphere, and corona undergo different changes, form quiet and calm violent activity all throughout the star itself. This is where we get sunspots. I mean, the height of the sun's activity is known as solar maximum. Solar flares, CMEs, coronal mass ejections, this is when it happens. The next high solar cycle for our sun is 2024. So we are going to be looking out for this. Because solar particles can damage power lines, the electrical fields of our own planet here. We will get about an 18-hour notification if a CME happens. I'm going to be putting a link in the description below in case anyone wants to help monitor and watch solar activities. Yes, it's actually a live event. People actually do this. It's public. Yes, thank you, NASA. I wanted to mention about Mr. Parker. The Parker Solar Probe. NASA launched the Parker Solar Probe on a mission to basically, they quote, touch the sun. This spacecraft right now is flying closer to the sun's surface than any other spacecraft before it. It's closer than Mercury itself. It's flying 7 times closer. Over about 7 years, the spacecraft will be completing about 24 orbits around the sun. And its closest approach to the spacecraft would be 3.9 million miles from the surface. It got launched on August 12th, 2018. This Parker Solar Probe here was basically known as faster than any other human object made. The PSP it also broke the record for the fastest spacecraft in history because on its final orbits, the spacecraft will reach up to, get this, 430,000 miles an hour. I mean, our ISS only orbits 15,500 miles an hour. This is fast. That's fast enough to travel from New York to Tokyo in less than a minute. I know the image is not to scale. I should have mentioned that. Thank you, Mike. I usually do, but thank you. The Parker Probe was named after Dr. Eugene Parker. He's the first person to predict the existence of the solar wind. In 1958, Dr. Parker developed a theory showing how the sun's hot corona, by then known to be millions of degrees Fahrenheit, is so hot that it actually overcomes the sun's gravity. According to his theory, the material in the corona expands continuously outwards in all directions, forming a solar wind. I mean, this is the first NASA mission to be named for a living person. And as an honor, Dr. Parker himself watched the launch from Kennedy Center in Florida. And that was an honor. I mean, we have unlocking the secrets of the solar system. I mean, even Dr. Parker predicted the existence of solar winds 6 years ago before we even discovered them. We had no idea that solar winds came in 2 distinct streams, fast and slow. But we've identified the source of the fast solar winds, but the slow solar winds is still a bigger mystery. I mean, right now, our only measurements of the solar winds happens near Earth. After it has tens of millions of miles to blur together, cool down and intermix. I mean, the Parker Solar Probe, the measurements of the solar wind, just a few million miles from the sun's surface. It's going to explore whole new regions of space. It's going to reveal new details that help us light on the mysteries of our own sun. I mean, we've had many missions to the moons, and just to name it, a couple here. As you can see, sorry, I've got to show this. This is actual a CME basically erupting from the surface of the sun and hitting the Parker Solar Probe. This happened on September 10th, 2017. You guys remember what happened in 2017 on the East Coast of Australia? Well, there was a little blackout. So this is very, very important that we predict the solar activity because we do not want to have another 1859 Parker Carrington event. We now have the Parker Solar Probe. There's been so far 20 operating missions with 27 spacecraft. 2 of them are currently in deployment, and 10 missions are in formulation, which means they're on the planning boards, on the drawing them out right now. Oh, you like that image? Yeah, this is actual video footage, by the way. You see the explosion, and all of a sudden the particles hit. We've had Hindoi. We also have Reishi, which is known as uh, the rover renderingly high energy solar spectral pop. I can't image it. You can read that, right? I can't talk right now. We've also got the SDO, the Solar Dynamics Observatory, SOHO, the Solar and Heliosphere Observatory, and of course, we have the Twins, which means we have a 360-degree view of the sun itself. I mean, our sun here, when it dies, what does it mean exactly? It's going to run out of fuel in its interior. I mean, it'll cease that initial thermonuclear reaction that enables stars to shine. It's going to swell into a red giant, which outer layers is going to engulf Mercury and Venus. And we're not exactly sure if it's going to take on the Earth itself or push Venus into the Earth, or it'll actually push Earth away. I mean, when sun-like stars run out of fuel, they explode in a series of pulses, throwing off much of the mass and giant formless shell of a gas called the planetary nebula. What remains of the star is a super dense white dwarf star. It's very, very center. The star's planets, if any, are shattered by the blast. It's all energy. I mean, stars begin their life cycles in nebula. For 50 million years, gas and dust collapse on its own gravity, heats up from friction. And of course, once the temperature and pressure is right for the nuclear fusion, the star itself ignites and hydrogen forms into helium. Ultimately, the star swells to huge size. The star, our sun, its radius will be twice the distance between Earth to the sun. I mean, this stage is basically, it's called the red giant phase. As our sun dies, the star will blow out most of its matter out into space, forming basically an expanding shell of gas. Sorry. At the end of its life, the star produced visible, though faint, planetary nebula, which that is, and more the fate of our sun here. Like I said, the surface of the sun is about 10,000 degrees Fahrenheit. I mean, the corona can't be much hotter than the sun's photosphere and atmosphere. And it is as hot as the convective zone inside the sun, which is about 3.5 million degrees. Most people think that the Earth is going to basically be swallowed by the sun. Well, I can tell you that will not happen. If the sun envelops the Earth will not be engulfed by the sun. This is actually what, here's the information here. This is exactly what will happen because the sun's corona is so hot, everything is going to melt before it even reaches the surface of the sun. We are going to fall onto dust, particles of dust onto the sun. So if anybody says the Earth is going to crash into the sun, that's not going to happen, okay? I just want to make that nice and clear for people. So that is not going to happen. I have that animation for Yvette Duvall. She's a quantum physicist. I had to talk about I have the animation for this. Yeah, this is what's going to happen to the Earth. So, hey, I want to thank everybody for joining me live. And if you haven't joined me live, you watch on the ReChat. That's why you ring the bell for notifications so you know when I do go live. Next week, we are going to have a little special wrap-up show. I'm going to be talking about some of the coolest things in our solar system. I'm going to have a top 10 list. Some of the coolest top 10 things we have in our solar system. Yes. So, if you want to watch this live next week, ring that bell. If you haven't already subscribed, make sure you hit subscribe. And say hi to everybody else in the chat. The sun only farts when it has a CME. So, yeah, it's called bad gas. There is gas involved. So, I want to thank everybody and have a good day.